Hello and welcome to Elements of Halton, the first teacher CPD for the project. I'd like to introduce myself. My name's Melissa Lord. I'm a trustee at Catalyst Science Discovery Centre, whose logo you can see on this slide. In 2019, there was a small project funded by the Royal Society of Chemistry with 2 Halton primary schools to celebrate the International Year of the Periodic Table in the context of Halton. The rich history of the borough shone through in that. There were so many amazing stories to tell that it would have been a pity to stop things there. So after a conversation with Cultivate, which is the local cultural educational partnership, and Halton Primary Arts Network, HPAN, and a grant application to the Royal Society of Chemistry, so lots of collaboration, we're really pleased to bring this to you. We're providing a range of resources for teachers involved in the project. These include this series of recorded CPD sessions, a teacher's pack available to download from the Cultivate website, and for schools taking part in the HPAN performance and working with creative practitioner Laura Hennessy, we're also providing resource boxes which will include materials for class activities, and these will be available in January 2021. So this is about science and heritage and stories, about the remarkable and innovative past of the borough. And we're aiming to link schools with STEM and with local heritage to show the significance of the chemical elements in the development of the borough, and to look at the science that all of this has been built on. There are 2 parts to the project: the chemistry behind it all, this part, and then separate stories to tell of some of the journey to the present. So we're learning from the past, we're thinking about the science of the future that's going to be so important for young people in school at the moment, and creativity and collaboration between them and one another as well in getting this story told. So what we're doing right now is we're looking at atoms and elements, because to understand the elements, it's helpful to start with atoms. This session, we're going to connect with the idea of atoms and elements and see if there's some surprising prior knowledge from the children in your classes. I found when I was doing the previous project that there often was. They knew of elements, they knew of ideas that I'd really not expected. We're going to look at how these ideas of atoms originate, what's some of the evidence behind them. We're going to talk about how atoms rearrange in chemical reactions and why that's important, and the sort of size of atoms. Try to get down our thinking to atom scale and what atoms do. Okay, our glossary. These are some of the words that are important in the story. There's a glossary for you in the teacher's pack as well. So these are the terms that we're going to be using along with compounds. Now, maybe there have always been people who wondered whether you could go on getting smaller and smaller amounts of stuff. We know about one person who had this idea. We know about him because other people passed his ideas on. He was Democritus. We don't know his first name. Ancient Greeks seem to have not had a first name like Jim. Anyway, he lived about 370 BCE. And he lived till he was about 90, so 2,400 years ago was his lifetime. We only know about him from what other people wrote, but apparently he was very jolly and his ideas were amazing. No one really knows what he looked like, but these are a couple of images to help. Now, Democritus wouldn't just believe something because he'd been taught it. He moved away from the ideas of the Greek gods that he'd been told of to the idea that there are natural laws, that there's cause and effect, and we can look for evidence. And because of that idea of looking for evidence, he's considered as the father of science. For instance, if he dropped his lunch in the river and the river carried it away, He knew the answer to why it was carried away was something about the position of his lunch in the river and the events that had gone before. The water pushed the lunch, and so the lunch got washed away, cause and effect. And explanations like this are the basis of modern science. He didn't believe that it was because the river gods were angry, so I'm afraid he gave the Greek gods a bit of a push. And another idea that he thought didn't hold was the idea that the Greeks had thought that there were 4 types of element: earth, wind, fire, and water. He said, nah. He decided everything was made of atoms, and these are his ideas of atoms, that atoms are physically indivisible. Atmos means uncuttable, so not made of smaller parts, that atoms, he said, can't be destroyed. He said atoms are infinite in number and variety. He said that atoms determine the behavior of a material. Iron's tough because the atoms hook together, he said, and water flows because the atoms are round and slippery. He said that atoms determine taste and that lemon atoms somehow manage to tear at the tongue. And it's perhaps worth asking your class if scientists still think that atoms are as Democritus described them, or whether they think that ideas about atoms have changed after 2,400 years. We've made an appendix for you about that. Democritus not only thought about the tiny scale, he looked at the sky and he wondered whether the wispy band of light that crosses it at night was actually made up of a huge number of stars at vast distances, so many, so far away that they blend into one. So we've got this picture of the Milky Way, or the Galacta, as they called it in Greek. He couldn't test his idea, so it wasn't really science, and it couldn't be tested until about 1600, when Galileo Galilei in Italy turned a telescope to the skies and found out that Democritus was right. Now, Democritus thought that the smallest bits of stone were stone atoms. That's Norton Priory, and this is my cat. He thought the smallest bits of fur were fur atoms, but there aren't stone atoms and there aren't fur atoms. But what maybe would be good to show your class is this video from Atomic School. Atomic School's from Australia. It's for primary schools. The RSC mentions it, links it on their website. And it's 15 minutes, that's all long. You might like to show it to your class. You make your own judgment about whether to do that. But we're going to carry on our story of the idea of atoms with Johannes Kepler, who lived about 400 years ago. He'd got a brilliant mind, and he was employed as astronomer and mathematician to various wealthy people in Europe. And in 1611, he found that his boss was the Holy Roman Emperor Rudolf II, who lived in Prague, in what's now the Czech Republic. Rudolf II, unfortunately for Johannes, wasn't very good at paying people. And Johannes, in turn, didn't have money to buy New Year presents for his friend. And he really wanted to give one of his friends something to mark the New Year that year, and decided that instead he could make it. And maybe what he'd do was write a book. And his inspiration was walking over this bridge in a snowstorm in Prague. The snowflake fell from the skies, and he wondered about his shape. He wondered in Latin, but here it is in English. Here was something smaller than any drop, but with a pattern, all coming down from heaven like a star. Why did it have this form? Was that hexagonal form connected with hexagons elsewhere in nature, like honeycomb in beehives? Was the water made from tiny particles that were stacking together in a regular way? So the previous slide links to a lovely video where you can watch snowflakes form under a microscope. And I think that would be a lovely thing for your class to watch and just see that six-fold symmetry come out. Now, Johannes knew that cannonballs for the army and oranges for sale could be stacked only in certain ways. He'd already written to people about this, and here's something from one of his letters. He'd noticed that some types of ways you stack things or packing give less space between the balls being stacked than others, and one of the best ways was a pyramid. He drew that, and the oranges are showing that. And when he noticed the stunning symmetry of the snowflake, he connected with this and wondered, was there a tiniest amount of water that Democritus would have called a water atom, that we call a water molecule, that was packing together in a regular way? What was going on? Now, what we've shown there is really something that your class will have met in maths, of tessellation, but in 3 dimensions. So tessellations are maybe a great way of linking this project with maths. And here's something to show that sort of idea, but happening with bubbles. On the right-hand side, we've got chaos. On the left-hand side, we've got regular bubbles and a pattern. Maybe the children can link why that happens there. It's very difficult, by the way, to set up this sort of situation. It's very hard to get those regular bubbles. And if they look, could they see the hexagons that are forming in that pattern on the left? This is a salt crystal image, the cubic structure seen under a really powerful microscope. It's been known for hundreds of years that salt and sugar always have cubic crystals. Is this because the particles inside, the sodium and the chlorine atoms, are stacked together in a regular way? So scientists in Kepler's time didn't know about sodium and chlorine atoms, but they wondered this. And this is an image that I've taken just with an iPhone with a macro lens attached. And we're providing you with a macro lens in your pack for schools. Some of the grains of salt are a bit chipped, but can you see that lots of them are cuboid? So you could try that with one of the school tablets. If you've got one, the macro lens should just fit to that. And that's granulated sugar. Don't use castor, use granulated. It's got bigger crystals, and I think that those are rather beautiful. So next place, how many sorts of atoms are there? Well, this is what the periodic table summarizes. Dmitry Mendeleev in 1869 noticed that if he put the atoms in order of their size, there was a pattern apart from size beginning to show in the way that the atoms behave. This is the periodic table. There are 118 known types of atoms. Some of them have had to be made artificially by very complex means, but in nature, there are about 90 different atoms, some of them in only tiny quantities. But this is at the basis of chemistry, and some of those atoms in the periodic table are our elements of Halton. They're the atoms that have made the borough, though there's an increasing number of them being used. I'm just going to go on to some terms that are going to be very useful in elements of Halton. That in particular is alkalis, but we'll mention acids as well. Now, foods that contain acids are tangy. It's the acid that gives them the sour tang, and the more acidic, the more tangy. Most of our foods are acidic, and some acids are vital, like vitamin C. In our DNA, the A stands for acid. But some other acids can be dangerous because of the way they react. We say that those are strongly acidic. Dangerous acids can have uses in industry. We'll meet some of those in the stories. So some acids need to be treated with care. Baking soda, which is sodium bicarbonate, is an alkali, and lots of the story of Halton is about factories where soda ash, the stronger alkali than the sodium bicarbonate, was made. Not many of our foods are alkalis, but some household products are alkalis, and strong alkalis like oven cleaner can be really dangerous, and eye protection and so on are needed with those. Water is neutral. It's neither acidic nor alkaline. In the chemical reaction between an acid and alkali, as with 2 of the experiments that we're going to suggest you link to, the 2 react together to produce new substances, and water is one of those. Indigestion results from too much acid in the stomach, and a cure is to take a mild alkali for that. Can we see atoms? We say atoms are microscopic, so if we look down a microscope, can we see them? Well, no. When we say atoms are microscopic, we mean that they're too small to be seen with a naked eye. The thing is, they're too small to be seen with a microscope as well, because microscopes rely on light, and the wavelength of light is thousands of times bigger than atoms are. So we can't use those. But near us in Daresbury, there is something that can be used. It's got the complex name of a scanning tunneling electron microscope. That can get down to the scale of atoms and reveal beautiful images like this one, which is of graphene, a form of carbon, a bit like the stuff in the writing part of a pencil. And if you look at that, the white dots that you can see in that lovely image, notice the hexagons again, those are carbon atoms. So a lovely link there with the previous story. And this is how we picture a crystal of salt, of sodium chloride. The atoms stacking in a regular array, the sodium and chlorine. So the elements are materials with just one type of atom. We've had a look at sodium chloride. That's not an element because there are two types of atom. It's a compound. There are the reactive element sodium's atoms there. You wouldn't want to meet sodium. It's very reactive. It would catch fire if it's near water. And you wouldn't want to meet the other element, chlorine, on its own. It's a gas, a toxic gas. But together, reacted together, combined together, those make that sodium chloride. It's worth asking if the class know the names of any of the elements, maybe at this sort of stage, to see what prior knowledge they've got. Like say, they might surprise you. Just another little bit of vocabulary. Pure in science has a different meaning from everyday life when we might talk about pure orange juice, meaning that that has just come from oranges in our everyday life. But in science, well, it's a mixture. We've said there's vitamin C. It's got water in, it's got sugar in, it's got all sorts of things. So in science sense, it's not pure. In pure oxygen, the only atoms present are oxygen. In pure water, all of the molecules will be H2O. There'll be nothing else. So a definite meaning there. And our story of atoms, our modern theory of atoms, to bring it more up to date, began with John Dalton in Manchester in 1803. He described how atoms combine together in fixed proportions. For instance, in water, there are 2 hydrogen atoms to every atom of oxygen. He noticed that from experiments, those sorts of patterns. He couldn't see atoms, but he deduced that. So he was gathering evidence. And yeah, different types of atoms, some slides now made from the Wollonk periodic table, which is on Creative Commons. We can show children designs like this and just get them familiar with some of the atoms that they've probably heard of. Helium is far too precious for balloons. It's got lots of uses and it's very scarce. Carbon, basis of the molecules inside us and of all living things, oxygen in the air. And we've mentioned sodium and chlorine in salt. And calcium, some of the children might have heard of. We need that for healthy bones. And iron's an element. Lovely steel structure there looking like the Jubilee Bridge. And each type of atom is called an element. And there are some to that if you wish. This is a second video you might like to show, 15 minutes again from Atomic School. So maybe take a look and decide if that's useful. So the last thing that we're going to do on the purely atoms theme, the STEM theme, is to think about how big atoms are. And it's about a sense of scale. Now, pupils in pairs will need 2 sheets of paper. In the teacher's pack, we've suggested A1, in which case you'll end up with something size A2 for display. When I was doing this, I used A3 and I ended up with A4 for display. The other things that the children will need are scissors, ruler, pencil, and a glue stick or paste. Start off by cutting or tearing through the long side of that sheet. And the yellow sheet is a half of the original. So 2 pieces of the yellow fit into the original. Cut along the long side again, like that, and 4 pieces of the yellow fit into the original. Cut again along the long side and 8 pieces fit into the original, and so on. And after 5 cuts, 5 halvings. We've got 32 go into the original. Let's carry on and do 10 halvings. So tear 7 gives 128, tear 8, cut, would give 256, 9 would give 512, 10 would give 1024. And it's a bit small to see. But what I've done here is a stop motion video. So let's see if we can get this to work. So cutting, 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 cutting. And after 10 cuts, my little bit of paper is just a bit smaller than 1,000th of the original. Okay, so I've got the 2 stacks. Now watch. Pairs of children can do this, swapping pieces with one another. And there'll be one tiny bit left over at the end, which is just a bit smaller than 1,000th of the original. Actually, the piece on top is a 512th of the one at the bottom. So if they cut that again, they'll get the piece on top to be 1,000th of the one at the bottom. Now, why have we done this? It's to give that sense of scale. All that process has taken us down 1,000-fold, a bit less, to a bit smaller than that. We are not at the scale of atoms. We're far from it. If we divide by 2 10 times, we go a bit tinier than 1,000 times smaller. To get down to atom size, imagine taking that tiny piece of paper on the top and carrying out the process again with that. We'd have to do that again 7 times. So all in all, starting with our original A1 piece of paper, we'd need to divide it by, I have to say this carefully, I'll do it in millions, 1,000,000, million, million, million times. And we get down to something like atoms. They're so small. So no wonder they need those special microscopes at Daresbury. Okay, atoms in materials can react. There's some suggestions here. There's some lovely suggestions on a link that's in here, and it's in the teacher's pack, to chemical reactions, videos made at Catalyst, irreversible changes. It links with the Key Stage 2 programme of study on irreversible changes, as I've mentioned. And we're suggesting that there's this freaky hand experiment. There's another one on candles, and there's another 2 that involve candles, actually, that are good to do. There's a risk assessment needed. We believe that they're absolutely safe, but do carry out your own risk assessment. We've put some leaflets in the box as well. And they're ones that you can demonstrate to the class quite nicely. So what's going on in any chemical reaction is it's as if the atoms in the original materials have done a dance where they've exchanged partners and they've formed something new. In the freaky hand, there's the gas carbon dioxide that's gone into that glove. And yeah, Legos maybe is a good model for atoms. Can the class say what they would do to model what an element would be like, given all that jumble of different Lego, and come up with the idea of pulling out all the same shape and the same color to model an element? Here's a model of a molecule, and it's quite nice to ask the children how many elements are in there, how many atoms in there, and yeah, how many molecules. It's just one. Or maybe to do the same thing with carbon dioxide and say what's going on. Do they get the idea? This is going beyond primary school science. It's quite nice taking them that bit further. But the important stuff for chemical reactions, we've got atoms as building blocks of all this stuff, and there's a limited number of types of them. That atoms rearrange and stick together in new ways, making new materials, and that has been so important for Halton. Let's just have a look at the crest of Runcorn and see how it's celebrated there. Well, the crest has got waves on it, 4 blue and white waves for the 4 waterways: the Mersey, the Bridgewater Canal, the Ship Canal, and the Weaver Navigation. the red colour for the local sandstone and for the fires of the chemical plants. Runcorn used to be a shipbuilding town or village, and there's a ship on there. Shipbuilding was important to the 19th century, the wheat sheaf of Cheshire. And interestingly, we'll meet it in another story, the two knives on there are the knives of St. Bartholomew, the patron saint of tanning, leather makers. And the motto, Navem mercibus in pleri, means fill the ship with goods. Widnes, its crest, it's got the red rose of Lancashire, the bees and beehives for industry. And the phrase on it is industria ditat, which means industry enriches. And it's got the kiln and the chemical vat on top as well, representing particularly soap and alkalis as the local industries. Combined in Halton for the two, with the Lancashire roses and the wheat sheaf in Cheshire, Industria Navem implet, industry fills the ships, and the bridge there is the Jubilee Bridge across the Mersey. And all of that's important, and it has been. That image is of soap works in Runcorn along the Bridgewater Canal in the 19th century, where alkalis too became important. The tanneries, that's Highfield Tannery in Runcorn, making more leather in Runcorn than anywhere else in England, skins from Cheshire dairy cows, boots for the army, including the Wellingtons for Wellington at Waterloo. And Kastner Kellner Works now at Western Point, a big Runcorn employer using brine from Cheshire, making chlorine for lots of new uses. And the Baker Gallery at Catalyst celebrates that. So maybe visit there sometime to find out more. And the Daresbury Science Park, including Daresbury Labs, where new materials are devised for the future, discovering molecular structure, for instance, of viruses that are changing our lives, making computers faster by the structures, the material science that goes on there. So give your class this type of quiz, see what they can remember if you like. But the important thing is knowing about atoms is really such a significant part of Halton, and a quiz for the elements just to finish off with the elements hidden. That might be useful to take the slides from there for your class. So thank you for listening, and I hope that's useful, and do get in touch if you'd like to find out more.